Welcome to The Deep Dive, the show where we distill groundbreaking research into the essential insights you need to stay ahead.
Glad to be here.
Today, we're plunging into one of the most pressing challenges in large language model development, LLM development. How do we efficiently adapt these powerful models to specialized downstream tasks?
It's a challenge we see pretty much across the board. While traditional reinforcement learning methods, things like GRPO, group relative policy optimization,
Right,
they're powerful for fine-tuning LLMs, no doubt.
right.
But their practical application is often severely hampered.
How so?
Well, by their computational intensity and, frankly, remarkable sample inefficiency.
Sample inefficiency, meaning they need lots of examples.
Lots and lots. We're talking about training processes that frequently demand tens of thousands and sometimes even hundreds of thousands of rollouts.
Hundreds of thousands, that's huge.
It is, to achieve effective adaptation and optimal performance. And this isn't just a theoretical hurdle, right? It creates a significant bottleneck for real-world deployment.
Leading to high costs, I imagine.
Astronomically high operational costs,
Yeah.
severely restricted inference budgets. And it makes it virtually impossible to fine-tune the weights of the very largest, most capable LLMs within practical constraints.
That's a critical limitation then for moving from research labs to, scalable real-world systems.
Absolutely.
But what if we could radically reduce that computational overhead? Our deep dive today centers on a novel prompt optimizer named GPA.
GPA stands for Genetic-Pareto.
Exactly. And GP fundamentally rethinks the conventional wisdom, the idea that we need these sparse scalar rewards to optimize LLMs.
Right, the single number reward.
Instead, it leverages the inherent interpretability and, well, the richness of language itself as a superior learning medium.
Which is a really interesting angle, using language to improve language models.
The promise here is genuinely transformative, achieving substantial quality gains with just a fraction of the rollouts traditionally required.
So our objective for this deep dive is to give you a professional, really comprehensive overview of GPA. We're drawing exclusively from the insights presented in the research paper.
Sticking strictly to the source.
Strictly. We'll meticulously explore its core principles, dive deep into its intricate mechanics, analyze its empirical performance across a diverse set of benchmarks,
Okay.
and even touch upon its promising extended applications beyond just initial task adaptation. Every detail we discuss will be directly substantiated by the research, ensuring you get the most accurate and in-depth understanding.
Fantastic.
Yeah.
So let's begin by fully understanding the problem statement that GPA seeks to address, this inherent bottleneck that reinforcement learning imposes on LLM adaptation.
Okay.
It's important to recognize, I think, that LLMs are increasingly not standalone monolithic things.
No, not at all.
Instead, we're seeing their sophisticated integration into what the paper calls compound AI systems.
Compound AI system.
Yeah.
Right.
These are intricate modular architectures where the LLM's natural language behavior specification is combined seamlessly with external tools and resources.
So think LLMs interacting with retrieval systems or executing code.
Or interfacing with external APIs to accomplish complex tasks.
Yeah.
Exactly.
Precisely. And in such compound AI systems, optimizing the LLM's performance for a specific downstream task isn't just beneficial, it becomes absolutely critical for the system's overall efficacy.
Makes sense. The whole system needs to work together.
Exactly. And for quite some time, reinforcement learning with verifiable rewards, or RLVR, has emerged as a prominent approach for this optimization.
RLVR.
Yeah, this category includes algorithms like GRPO, which has gained significant traction. The underlying mechanism is conceptually pretty straightforward.
How does it work?
Success metrics are basically translated into a single scalar reward, just one number, observed at the end of each rollout.
And a rollout is?
A rollout, in this context, is one complete execution path of the LLM system on a given task instance. It includes all its internal reasoning, any tool calls it makes, and the final output.
Got it.
These observed scalar rewards are then used to estimate gradients, which in turn guide the LLM's policy toward improved behavior. Standard RL stuff, fundamentally.
And this is where we hit that core inefficiency that GPT is trying to get around.
Exactly. While RLP approaches like GRPO can demonstrably improve performance, they typically demand an extraordinarily large number of rollouts to successfully converge and adapt to new tasks in practice.
The paper really emphasizes this point, doesn't it?
It does. It starkly highlights this, citing compelling examples from recent work using GRPO, where training needed anywhere from tens to hundreds of thousands of rollouts.
Those are not trivial numbers. That's immense computation.
Immense. especially considering the scale of modern LLMs and the complexity of the tasks they handle.
So what are the practical ramifications of this sample inefficiency for real-world LLM applications?
They are profound and far-reaching. Firstly, think about the financial side. Many external tool calls, like using sophisticated APIs or complex database queries, often cost money per invocation.
Right, API costs add up fast.
They really do. When you're talking tens of thousands of these calls, the operational expenses can quickly become prohibitive.
Okay, cost is one factor. What else?
Secondly, even without direct API costs, there's an inherent limited inference budget for sampling from the LLM itself, especially for the big proprietary models where every token generated costs compute and money.
True.
And perhaps most critically, for the very largest and best LLMs available today, it's often computationally infeasible to fine-tune their entire weight parameters directly using these high-sample RL methods.
So developers are stuck?
Pretty much. It forces them to either rely on less efficient prompting strategies, which might not unlock the model's full potential, or to use smaller, less capable models, which compromises performance.
This brings us neatly to the foundational insight underpinning the whole GPA framework. Though the research paper suggests we might be overlooking a critical advantage by squashing all that rich, detailed information from an LLM's execution into just one single sparse scalar reward.
Right. Losing information in the compression.
Exactly. What the researchers observed is that the complete trajectories or traces from these LLM systems, even complex ones doing multi-step reasoning or tool use, can be serialized into remarkably interpretable sequences. We're talking natural language, even formal language sometimes.
So not just the final answer, but the whole journey.
The whole journey. Imagine having the LLM's internal instructions, its step-by-step reasoning chains, the specific tool calls it made, the raw outputs it got back.
Even things like compiler error messages if it's generating code.
Precisely. The detailed internal workings of the reward function itself, not just a binary pass or fail.
And this is the crux of GPA's innovation. Because these serialized trajectories are inherently understandable by modern LLMs, which are, after all, built on language priors.
Right. They understand language.
The paper argues that algorithms designed to learn directly from and through natural language by reflecting on these rich textual traces can make far more effective and efficient use of the LLM's inherent capabilities.
A stark departure from standard RL, which uses numerical rewards.
Completely. Standard RL largely operates on a much more abstract numerical representation. By working in the linguistic domain, GPA taps directly into the LLM's core strength, its ability to comprehend, process, and generate language.
So to make this insight operational, the researchers developed GPA, the Genetic-Pareto Reflective Prompt Optimizer.
And it's specifically engineered for these compound AI systems we mentioned.
Yes, seamlessly merging textual reflection with a multi-objective evolutionary search paradigm.
Okay, let's define compound AI system, precisely as the paper does. It's any modular system made up of one or more LLM calls.
Potentially interleaved with external tool calls.
And all orchestrated through some arbitrary control flow logic.
It's a broad definition designed to cover a lot of ground.
Right. Think complex agents chaining multiple steps, multi-agent systems where LLMs collaborate, or general scaffolding techniques like ReACT.
ReACT being reasoning and acting.
Exactly. Or Archon, another framework for system optimization. It covers a lot.
Paper formalizes this system too, right? As V, MCXY.
That's the one, where the dollar is the collection of language modules, each with its own prompt peen and waits till laterally.
Seer is the control flow, the logic dictating the sequence.
And a dollar is the global input and output schemas for the whole system.
So at runtime, this control flow dollar manages everything, calling modules, passing outputs, using tools.
Precisely. It handles the orchestration, passing outputs between modules, maybe calling them conditionally based on results, using external tools. It enables dynamic multi-step operations beyond just a single LLM call.
Given that architecture, what's the optimization problem GPA is actually solving?
The goal is to find the best set of parameters, denoted Langle pi, theta angle phi. That's all the module prompts and potentially the model weights.
Okay, find the best parameters to do what?
To maximize the expected output quality. Formally, theta angle phi and theta angle phi, averaged over some task distribution dollars.
But there's a critical constraint for GPA.
Yes, the sample-efficient optimization problem. The optimizer is strictly limited to a budget dollar of rollouts.
A fixed number of tries, essentially.
Exactly. So the challenge becomes paramount. How do you extract the absolute maximum learning signal, get the biggest performance gain from every single one of those potentially very expensive rollouts within that tight budget.
That really frames the challenge. So how does GPA actually achieve this remarkable sample efficiency? Let's get into the mechanics.
Okay. It's built upon three core principles working together: genetic prompt evolution, reflection using natural language feedback, and Pareto-based candidate selection.
Genetic, reflection, Pareto. Got it.
These are combined into an iterative process that lets the system continually refine its prompts.
Let's start with the genetic optimization loop. That sounds like the core engine.
It is. It's the iterative backbone. The process starts by initializing a candidate pool. Let's call it $10.
And what's in the pool initially?
It's populated just with the parameters of the base LLM system, the starting point. That's the first candidate.
And a candidate here means?
A candidate is a complete, concrete instance of all the learnable parameters in the compound AI system. Primarily, this means the set of system prompts for each LLM module.
Okay, so you start with one candidate, then what?
From there, GPA kicks off an iterative loop. In each cycle, it proposes new, hopefully more effective candidates and adds them to the pool.
And this continues until?
Until the predefined evaluation budget, Ditto to par, is completely used up. It's like an evolutionary algorithm creating and testing new generations.
How are these new candidates generated? Through evolution, you said.
Right. They're mainly created by modifying existing good candidates already in the pool. This happens through two main mechanisms.
Mutation and crossover, like in genetics.
Pretty much. Mutation involves a targeted, single-prompt modification within one specific LLM module. Crossover is more complex, combining elements like prompt structures or learned strategies from multiple existing candidates to make a new one.
And this isn't random, it's informed by performance.
Absolutely. It's informed by the learning signals from new rollouts. GPA meticulously tracks the ancestry of each candidate.
Why track the ancestry?
It allows for the accumulation of lessons along the genetic tree. Each new candidate inherits insights and optimized prompt structures from its parents and the latest successful rollouts. It builds on past success.
Okay, so new candidates are proposed. How are they evaluated?
It's quite sophisticated. Each new variant is first evaluated on a small mini batch of tasks from the training data.
Just a quick check?
Exactly. If it shows improvement relative to its parents on that mini batch, is considered promising and added to the pool dollar.
And its lineage is tracked.
Crucially, yes. Its ancestry is recorded.
Oh.
And concurrently, a full evaluation is done on a dedicated validation set called a Pareto.
That sounds important.
Very. It plays a key role later in the Pareto-based candidate selection strategy, ensuring the optimization is effective in the long run.
So the loop runs, the budget depletes. What's the final output?
Once the budget bill dollar's gone, GDA doesn't just give you the last candidate it looked at. It systematically returns the candidate that showed the best aggregate performance on that period of validation set across the entire process.
So the most consistently good one found.
Exactly. It ensures the final output is robust, not just a temporary blip.
Now let's dive into what really makes GPA different. Reflective prompt mutation. This is where that language advantage comes in, right?
This is absolutely where it comes into play.
Yeah.
The natural language traces from the system's execution offer exceptionally rich, granular visibility into how each module behaves.
We're talking intermediate inferences, reasoning steps, tool outputs.
Everything.
And when you pair these detailed traces with the final outcome, success or failure,
they provide huge diagnostic value.
Yeah.
This granular insight allows for much more precise credit assignment.
Meaning you can pinpoint where things went right or wrong.
Exactly. You can trace errors or successes back to specific decisions or prompt elements at the individual module level. And critically, LLMs themselves are used to perform implicit credit assignment through reflection.
The LLM reflects on its own trace.
Or rather, a meta-LLM reflects on the trace of the system being optimized. It's not just about what happened, but deeply understanding why, based directly on the language in the trace.
Okay, operationally, how does this reflection-driven mutation work? Walk us through the steps.
Sure. GBA first selects an existing candidate from the pool to mutate. Then it picks a target module within that system to improve, maybe using a round-robin approach to hit all modules eventually.
Okay, candidate and module selected.
Then GPA generates a few rollouts using that candidate on a small mini-batch from the training data. It records the outcomes and, importantly, the full execution traces.
Capturing all that rich linguistic data.
Precisely. By examining these traces, GPA identifies the target module's specific inputs, its outputs, and the reasoning process it used.
Got it. Now the reflection part.
Now the reflection.
Oh,
An LLM, the meta LLM, is prompted to examine all this information. It attributes successes or failures to specific elements or maybe omissions in the module's current prompt.
based on the trace and the outcome.
Right. Based on this deep linguistic reflection and diagnosis, the meta LLM proposes new, refined instructions for the target module.
Creating an improved prompt.
Exactly. This updated prompt forms a new candidate, essentially an evolved version of the system, but with one module's prompt intelligently revised based on learned lessons.
That's really clever. And there's this enhanced feedback function. What's that about?
Ah, yes. No bed. This is another innovative aspect. Beyond just the system's internal execution traces, the evaluation process itself can generate highly diagnostic info.
Like compiler errors.
Exactly. Think about evaluating code. It doesn't just return pass-fail. You get compilation output, runtime errors, profiling data, often as text.
Which usually gets collapsed into a single score.
Right. But GPA leverages these textual cues. This new function is designed to return not just the final score, but also feedback text.
Providing granular, module-level feedback when available.
Precisely. It could be a specific compiler error, or maybe feedback in a multi-hop reasoning task, pinpointing where a logical step failed.
The paper's appendix has the meta prompt, right? The instructions for the reflecting LLM.
Yes, Appendix B.
Yeah.
It's quite detailed. It includes directives like read the inputs carefully and identify the input format and infer detailed task description.
So it's guiding the reflection process.
Very explicitly. Another part says read all the assistant responses and the corresponding feedback. Identify all niche and domain-specific factual information included in the instruction. The assistant may have utilized a generalizable strategy. Include that in the instruction as well.
Wow, it's actively telling the LLM to learn from both mistakes and successes and generalized strategies.
Exactly. It goes way beyond simple numerical updates. It's about linguistic comprehension and self-correction.
A profound shift. Okay, let's move to the third core principle, Pareto-based candidate selection. Why Pareto? What problem does this solve?
This is crucial for escaping local optima. A common pitfall in complex optimization, like prompt engineering, is getting stuck.
How does that happen?
Well, a naive strategy might be always select the best performing candidate found so far. Just keep tweaking the current best.
Seems reasonable.
It seems reasonable, but it can easily trap the optimizer. Imagine a landscape with hills and valleys. This strategy climbs the nearest hill, finds its peak.
And then gets stuck there, unable to see taller hills elsewhere.
Precisely. It leads to budget exhaustion without exploring potentially much better strategies hidden elsewhere in the search space.
So GPA uses a Pareto-based approach, what they call the illumination strategy, to avoid this trap.
Right. Instead of just tracking the single best overall candidate, GPA constructs a Pareto frontier of scores.
How does that work?
It identifies the highest score achieved for each individual training instance across all candidates currently in the pool.
For each task separately.
Yes. This preserves a diverse set of winning strategies. A candidate might be the best on task A, while another is best on task B. GTPA keeps both. It recognizes multiple paths to success.
So it compiles a list of these winners.
Exactly. It compiles a list of candidates that achieve the best score on at least one training task. Every valuable insight is preserved.
Then there's pruning.
Yes, a crucial pruning step. Any candidate that is strictly dominated by another is removed.
Meaning?
If candidate 3 is better than candidate 2 on task 1 and is also the best on task 2, then candidate 2 is removed. It's strictly inferior to an existing option. This streamlines the pool without losing good strategies.
Okay, so you have this prune list of Pareto optimal candidates. How do you choose which one to mutate or cross over next?
This is key for balancing exploration and exploitation. GPA stochastically samples a candidate from this pruned list.
Randomly.
Not quite randomly. Candidates that perform best across more training instances are giving a higher probability of being selected. It introduces intelligent diversity.
So it favors broadly successful candidates, but still gives niche winners a chance.
Exactly. This sophisticated strategy is what empowers GPA to effectively escape those local optimics. The paper shows this clearly.
How so?
Compared to the naive select the best approach, which quickly stalls, Pareto-based sampling creates a much more balanced, expansive search tree. By considering all Pareto optimal candidates, it ensures continuous, robust improvement within the budget. It finds better solutions overall.
This all sounds incredibly promising in theory. Let's turn to the empirical evidence. How did GPA actually perform in tests?
The evaluation setup was rigorous, detailed in the paper. They used a standard three-way data split, training data, fully accessible to the optimizer.
A validation set for candidate selection and early stopping, but with restricted content.
And a held-out test set, used only for the final, unbiased assessment after optimization. Standard good practice.
And they tested it on diverse tasks, right? To show it's not just a one-trick pony.
Absolutely. 4 diverse tasks, crucial for showing broad applicability. First, hotpot QA.
Multi-hop question answering needs reasoning over multiple documents.
Right. They used a modified hover multi-hop program. Yeah. And importantly, the textual feedback mechanism identified relevant remaining documents, a rich signal for reflection. They used 150 train, 300 validation, 300 test examples.
Okay, what was next?
IF bench. This focuses on strict instruction following with precise output constraints.
Tricky.
Very. The test set was extra challenging, with new, out-of-distribution constraints to really test generalization. The feedback described exactly which constraints were met or failed. Again, 150 train, 300 val, 294 test examples here.
Third.
Hover. Open domain multi-hop fact extraction and claim verification. Here, they evaluated the system's ability to write good queries to find relevant Wikipedia documents.
And the feedback.
Identified correct or remaining documents needed. Similar setup. 150 train, 300 val, 300 test.
And the last one.
PUPA. Privacy-aware delegation. This is more complex, a multi-objective task.
Balancing quality and privacy.
Exactly. Balancing response quality against minimizing PII leakage. They used the Papillon compound AI system for this. The feedback broke down the aggregate score into quality versus PII leakage components. Fewer examples here. 111 train, 111 val, 221 test.
That's a really diverse set. Covers reasoning, constraints, information retrieval, multi-objective optimization.
It really does. A thorough test bed.
What about the LLMs used? Did they try different ones?
Yes, a smart mix. For open source, they used Qwen3 8b, standard decoding settings, 10.6, top P 0.95, top K 20. This was specifically used for the GRPO baseline experiments.
And proprietary models.
They tested GPT 4.1 mini via the OpenAI API with temperature 1.0. This provided a comparison against a leading-edge model. Shows adaptability.
Okay, models covered. What about the optimizers they compared against? The baselines.
Several crucial ones. The fundamental baseline was just the baseline, the unoptimized program. Right, then in IPOF2, the paper calls this a state-of-the-art prompt optimizer. It uses Bayesian optimization to jointly tune instructions and few-shot demonstrations and prompts.
So it optimizes both parts of the prompt.
Yes. Its rollout budget varied by benchmark, from about $2,200 for PPA to nearly $7,000 for Hover, reflecting its typical usage.
And the main RL comparison.
That was GRPO, Group Relative Policy Optimization. They implemented it with LoRa for efficiency rank 16, alpha 64, dropout 0.05.
LoRa helps reduce the fine-tuning cost.
Exactly. GRPO ran for a fixed 24,000 rollouts over 500 training steps. This provided a direct, controlled comparison against a well-known RL approach.
And finally, GGPA itself. 2 variants.
Yes, GPA and GPA plus merge. Both used a mini-batch size of 3. GPA plus merge invoked its special merge strategy up to 5 times.
And crucially, how did its budget compare?
To ensure a fair fight with MIPRAV2, GPA's total rollout budget was meticulously capped to exactly match MIPO2's budget on each benchmark.
So any performance difference is down to the algorithm, not just more compute.
Precisely. A very fair comparison setup.
Okay, the stage is set. Let's get to the results. What were the key observations?
Let's synthesize the key findings from their tables and figures. Observation number 1 is huge.
Which is?
Reflective prompt evolution is remarkably sample efficient and consistently outperforms weight-based reinforcement learning like GRPO.
Outperforms RL and uses fewer samples.
Yes. Across all 4 diverse tasks, GPA showed robust generalization and incredibly rapid adaptation within those compound AI systems.
That's a major finding. Let's see the number.
Quantitatively, GPA consistently beat GRPO, which used 24,000 rollouts with LoRa, by up to 19%. On average, it was about a 10% gain across tasks.
Impressive gains. And the efficiency.
This is where it gets really compelling. GPA achieved these better results using up to 35 times fewer rollouts.
35 times fewer. Wow. Can you give specifics?
Sure. On hotpot QA, GPA scored 62.33 versus GRPO's 43.33. That's plus 19%. GPA used only 6,438 total rollouts.
Yeah, okay.
IF bench. GPA 38.61 versus GRPO 35.88. A smaller gain plus 2.73%, but GPA used just 6,858 rollouts.
So it's incredible efficiency.
You hovered here. GPA 52.33 versus GRPO 38.6%. That's plus 13.66%.
Yeah.
GPA used 6,858 rollouts.
Still way less than 24,000.
Way less. And PUPA, GPA 91.85 versus GRPO 86.66, a plus 5.19% gain. GPA needed just 2,157 rollouts, 11 times fewer.
This translates directly into massive cost savings and faster development, doesn't it?
Absolutely. It's a game changer for practical applications.
The efficiency looks even better when you consider how quickly GPA matched GRPO's best performance, right?
Yes. On Hotpot QA, GPA matched GRPO's peak after only 402 rollouts, IF bench. Just 330. Hover. 11,179. PVPA. A mere 306 rollouts.
That translates to up to 78 times greater sample efficiency just to reach parity.
Up to 78x, yes, in terms of reaching comparable performance milestones.
And if you only count the rollouts used for learning, not validation.
Even more efficient. It needed only 737 training rollouts for Hotpot QA, just 79 for IF Bench, 558 for Hover, 269 for PPA to get its optimal result.
79 training rollouts on IF Bench, that's tiny.
Tiny. And to just match GRPO's best validation score, GPA sometimes used as few as 6 training rollouts on Hover, or 32 on IF Bench. It highlights the power of targeted learning via reflection.
What about the GPA plus merge variant? Did that help?
It solidified the findings further. It outperformed GRPO by an even wider margin, up to 21% better, at comparable total rollout budgets to standard GPA.
Noticeable on any particular task.
Particularly on IF Bench with GPT 4.1 Mini. It got an 8.16% gain even on the out-of-domain test constraints. Shows robustness from the merge strategy.
Okay, so observation 1. GBPA beats RL on performance and especially on sample efficiency. What's observation 2?
Observation 2 challenges some existing ideas. It shows that reflective prompt evolution, focusing only on instruction optimization, can actually outperform joint instruction and few-shot optimization strategies.
Meaning GPA beat MI-PROV 2.
Consistently, yes. GPA outperformed MI-PROV2, a state-of-the-art joint optimizer in all settings. Margins were up to 11.1% for GPT 4.1 Mini and 10.3% for Qwen 3 8B.
So optimizing just the instructions was more effective here than optimizing instructions plus examples.
In these experiments, yes. Looking at aggregate gains over the baseline, GPA and GPA plus merge more than doubled the improvement seen from MI-PROV2, plus 16.02% and plus 14.29% S plus 7.04%.
Why is this significant? Doesn't prior work often favor few-shot examples?
It often did. The paper suggests this shift is due to two things: recent big improvements in LLM instruction following capabilities and their enhanced self-reflective abilities. GPA's design really capitalizes on these advancements.
Any other evidence for this shift?
Yes, the generalization gap analysis. It shows that instructions evolved by GPA have a lower generalization gap. They perform better on unseen test data relative to training data compared to other methods. This reinforces the idea that the models in GPA are working well together.
And the prompts themselves look different.
Qualitatively, yes. Unlike some prior findings where instruction optimization might have created quasi-exemplars instructions acting like hidden examples, GPA's prompts often contain detailed, explicit, declarative instructions.
More like actual rules and strategies than just compressed examples.
Exactly, suggesting genuine linguistic learning of high-level concepts.
Okay, on to observation 3. This one's about the candidate selection strategy.
Yes. It shows that how you select the next candidate to work on strongly influences the optimization path and the final performance.
They did an ablation study, comparing Pareto selection to something simpler.
Right. They compared GPA's Pareto-based sampling with a naive select best candidate strategy, which just always picks the current top performer.
And the simpler strategy wasn't as good.
Not nearly. The naive select best candidate often leads to suboptimal exploration. It gets stuck in local optima.
It finds a decent solution quickly, but then stops improving.
Pretty much. It makes an initial jump, then stalls, wasting budget, trying to micro-optimize that one solution instead of looking elsewhere.
How did Pareto selection compare quantitatively?
GP with Pareto sampling significantly outperformed select best candidate by as much as 8.17% on some tasks, with an aggregate margin of plus 6.4% across all benchmarks.
Oh, why the difference?
Because Pareto sampling actively diversifies the search. By considering all Pareto optimal candidates, the winners on individual tasks, it ensures a better balance between exploring new areas and exploiting known good ones. It builds a more expansive search tree and finds better solutions overall within the same budget.
Makes sense. Observation 4. This sounds like a practical one.
Very practical. Instruction-optimized prompts are computationally cheaper and generalize better than few-shot demonstration prompts.
Cheaper how? Fewer tokens.
Exactly. Few-shot demonstrations can make prompts really long, especially if you need several examples, or if an optimizer like MIPRO2 tunes multiple demos. Longer prompts mean more tokens, higher API costs, more latency.
And GPA avoids this.
Yes. GPA's reflectively evolved instructions stay remarkably compact while delivering those big performance gains.
How much shorter?
Up to 9.2 times shorter than prompts from MIPRV2 in their tests.
Wow, nearly 10x shorter. That's a massive difference for cost and speed.
Huge impact. Lowers runtime cost, decreases latency, improves overall system efficiency. The paper even shows higher performance often correlates with these shorter prompts from GPA. It's a win-win.
Okay, final observation. Number 5. About crossover strategies.
Yes, specifically about system-aware crossover. They introduced a unique strategy called merge. GPA plus merge, using this strategy, could outperform standard GPA by up to 5% on some tasks, adding about 2% improvement overall.
How does merge work? Why is it effective?
It seems GPA plus merge can identify distinct optimization lineages that learn complementary strategies, maybe by evolving different modules independently. The merge operator then intelligently combines elements from these successful but different paths to create an even better combined solution.
Interesting, combining the best parts of different successful evolutions.
Exactly. However, it wasn't universally better for all models.
Oh.
While it worked great for GPT 4.1 Mini, it actually led to performance degradation with Qwen 3 8B overall, though it helped on one task.
So model dependent.
It seems so. This suggests that the optimal budget split between mutation and crossover, and when to invoke crossover, needs more study. Maybe adaptive techniques are needed.
Lots of rich findings there. Now, the paper also explores using GTA beyond just optimization for new tasks, right? As an inference-time search technique.
Yes, this is a really promising preliminary finding. The idea is to treat the specific tasks you need to solve right now, say, converting a list of PyTorch modules to CQA kernels, as the training set for GPA.
So drain a little by two, become the actual problems you want answers for.
Exactly. This lets GPA effectively overfit to this specific set of tasks. It iteratively proposes better solutions for each one, applying lessons learned from one task's rollouts to the others in the set.
Using the optimization machinery for real-time problem solving.
Precisely. They showed compelling examples in code optimization. First, NPU kernels for AMD's XDNA2 architecture using the NPU-IVL benchmark.
And the feedback mechanism was key here.
Critically important. It was used to dynamically inject domain-specific knowledge. For instance, compiler error messages triggered retrieval of relevant sections from technical manuals or architectural best practices.
Like a dynamic RAG feeding into the prompt evolution.
Exactly that. This promoted architectural best practices directly into the evolving prompts, leading to much better code.
What were the results for these NPU kernels?
Quite dramatic. GPT-4 alone, used with an agent called sequential 10 that iterates 10 times, got only 4.25% mean vector utilization.
Very low.
Adding AG improved it to 16.33%. Integrating MIPRO2 got it to 19.03%.
Okay, better, but still not great.
But GPA, running without an external RAG system during its process, boosted performance to a mean vector utilization of 30.52%.
That's a huge jump.
Huge. And some kernels reached up to 70% utilization. Even a single prompt generated by GPA when used by sequential 10 without RAG achieved 26.85%, driven purely by linguistic reflection and evolution.
They also tried it on CDA kernels.
Yes. For NVIDIA V100 GPUs using kernel bench, GPA with GPT-4o took GPT-4's initial near-zero FastP score, which measures how many kernels passed performance tests, to above 20% as the search budget increased.
Showing iterative improvement again.
Clearly showing iterative refinement and improvement of CDA code quality and efficiency.
These are really compelling early results for inference time use.
Highly compelling. It suggests GPA for inference time search, especially with rich textual feedback, could generalize to many other code generation and complex domain adaptation tasks. A very exciting direction.
Of course, no research is without limitations. What did the paper acknowledge?
They were candid about several things. One is the fundamental boundary between prompt-based learning and weight-based learning. It's still not fully understood.
When is one better than the other?
GPA excels when rollouts are expensive. But traditional weight updates might still win in data-rich situations, or when massive rollouts are feasible. They could be complementary.
They also mentioned a limitation with their GRPO baseline?
Yes, that they use LoRi for efficiency. Future work should ideally compare against full parameter fine-tuning for GRPO, though they note prior studies consistently needed 100,000 to over 500,000 rollouts for that. More GRPO hyperparameter tuning would also strengthen comparisons.
What about GPA's own scope?
Currently, it focuses only on optimizing instructions. Future work could explore adding few-shot demonstration optimization into GP's process. That might boost performance further on tasks that benefit from examples.
Any ideas for improving sample efficiency even more?
Yes, a lot of GPA's rollouts are currently used for validating candidates on the way to GPO. They suggest exploring the impact of the validation set size and maybe dynamic or subsampled validation strategies to potentially reduce this overhead.
And this idea of feedback engineering.
A fascinating underexplored area, systematically figuring out which parts of the system, execution, or evaluation traces provide the most valuable learning signals for reflection. Better feedback could lead to faster, more effective learning.
Finally, unifying prompt and weight optimization.
A key hypothesis for the future. GPA currently works with fixed model parameters. Could the language-based lessons from GPA be used to guide RO rollouts for weight updates? Combining these could yield additive gains, unifying the two approaches.
Okay, let's wrap up. What's the key takeaway on GPA?
To recap, GPA emerges as a novel, highly effective and crucially sample-efficient prompt optimizer for LLM agents and workflows. It's demonstrated superiority over methods like GRPO and sample efficiency, combined with robust generalization and outperforming other optimizers like MIPRv2, marks a significant advance.
And its success stems from?
Really, two pivotal innovations. Explicitly incorporating rich natural language feedback throughout the learning process and meticulously maintaining that diverse pool of Pareto-optimal candidates to avoid getting stuck.
These allow rapid, efficient, robust adaptation even when resources are tight.
Exactly, where traditional methods might be too costly or slow.
So this deep dive really shows GPA represents a significant step towards more human-like, adaptive, and efficient AI learning.
Definitely. Its core principles, language-driven reflection, Pareto optimization, are likely to inspire a lot more research into making AI systems learn better and faster.
Absolutely. And as you, our listener, consider the implications of GPA, maybe ask yourself this: how might these principles of natural language reflection and Pareto-based optimization, seen so powerfully here, transcend just prompt optimization? Could they fundamentally alter how we even conceive of learning within these increasingly complex modular AI systems? And where might that lead us next in the quest for truly adaptive intelligence?
A truly thought-provoking question that definitely opens up many future possibilities.
Thanks for joining us on this deep dive. We'll be back soon with another stack of groundbreaking research.